afternoon, everyone. So the topic is metal matrix, fiber metal, ceramic matrix composite for aerospace applications. So first, here is the content, as all of you can see. Well, 40 years ago, aluminium dominated the aerospace industry due to its low density, which makes it a suitable material for aerospace implementations. For instance, in the year 1970, the German scientists made the first full metal body aircraft, which was made from aluminium. In the year 1957, the first satellite launched by the USSR was also made from the aluminium alloy. But today, with the passage of time, a typical jet utilizes only 20% of pure aluminium. Now let us picture an example to see this. If we see Boeing 787, we can see in the red part of the chart that it utilizes 20% of aluminium. Now, in comparison to the previous version of the Boeing 777, we see that it utilizes 50% of aluminium. So, ladies and gentlemen, I believe you are astonished to see such a big change in the number and statistics due to the involvement of composites. Now, as I'm talking about composite, first let us understand what is actually a composite. A composite is made up of two parts, a matrix, which acts as a binder, and the reinforcement. And we can see over here that why we are talking about MMC, right? So let us see about what is actually a MMC. The matrix part of MMC is actually made up of aluminium, titanium, silver, magnesium, cobalt, nickel, and iron, whereas the reinforcement part is made up of ceramic particles and oxidized metal fibers. Now the question is, why among all the composites are we talking about MMC? In order to understand that, let us now investigate the properties of MMC which makes it a suitable material for the aerospace implementations. The first is that it has a lower coefficient of thermal expansion. It is stronger and stiffer than most other matrix. Moreover, it has got a high wear resistance. It is a ductile material. And it is also corrosion resistance. Now, as we see over here that these are the properties of MMC which makes it even more suitable than the base metal itself, which was used earlier. Now, I believe we all engineers love to see some mathematical statistics, mathematical data presented in a table. All of you, right? Sitting over here. So I thought of adopting some of the data, and the reference is given below, the source itself, as you can see over here. So here is a fiber part that is made up of many different materials, as you can see over here. And here is the matrix part, and you can see over here that here is a fiber content, which is also given. Now, the data associated with it is the longitudinal tensile strength. So, I believe we have plenty of numbers to work with, but until and unless we put those numbers in a frame of picture, let us visualize what it comes out to be. As we see over here, this is the longitudinal tensile strength with respect to the fiber content in percentage of the volume. If we see this, as a designer, I would be very happy to see such a beautiful graph. You know why? Because if I'm looking for a longitudinal tensile strength at a very high longitudinal tensile strength, I will be definitely looking and keeping my eyes at the top of the graph. And I'm looking for a very smaller amount of longitudinal tensile strength, I will definitely be looking at the lower part of the graph. Now, why I'm doing so? Why I'm doing these things? Because I want to select the appropriate material for my design. And as a designer, I can select the appropriate material from the data itself whenever it is presented in this form. Right? So according to the requirement, basing on the requirement, we can actually choose the right MMC suitable for us, for the designer. Now here is another thing. Always we, the aerospace engineers, and I can see over here there were also presentations made by aircrafts, remote control aircrafts, RMC. Well, what I understood that the biggest challenge for any aerospace engineers, the million-dollar question has always been how to reduce the weight. Well, the answer can also be solved utilizing the MMC. The horizontal axis over here, as you can see, the silicon carbide reinforcement content, as well as in the y-axis, there is a density change. Now, the thing is, I'm choosing various type of metal. say for instance, magnesium, magnesium, aluminium, titanium, and the nickel superalloy. Now, what should I do with this graph, with this data? First of all, let me imagine that I want to keep my reinforcement part content a constant. If I do so, and I start drawing a line from exactly 20% over here, and as a designer, if I choose magnesium as my matrix part, then of course I will be getting the most highest amount of weight for my structure. Now, basing on the requirement and basing on the type of design I want to do, if I just put the metal matrix as aluminium, I can reduce the density even less, right? And even if I choose titanium, I can even reduce it to much lower. Similarly, the best option would be nickel superalloy. But the thing is, basing on the design requirement and the manufacturing cost itself, a designer can look at and find the appropriate MMC that can actually reduce the density. Now, coming to the fact that I've been discussing a lot about MMC, let us see the practical implementations why our paper focuses much on MMC. Previously, the two vertical fins of F-16 fighting Falcon aircraft was made from aluminium alloy. And you know what it resulted in? It resulted in aerodynamic buffeting and it caused fatigue. And you know the next thing what it was done? There was a slight modifications being made. And the modification is in the selection of material from the base metal itself to the MMC. After this was done, you will be astonished to see such a huge and big change in the number itself. The tip deflection reduced by 50%. The buffeting, which was done earlier due to the utilization of aluminium, have stopped, and the life service was extended over 400%. So you can see over here, and much more important is that the inspection and the maintenance costs were reduced, and it saved around $26 million. So you can identify the fact of why we are talking about MMC as a suitable material for our aerospace implementations compared to the base metal itself. Now the next thing is, when I was very young, my mom used to say, if you are good, try to be better. If you are better, try to be best. So we should also investigate some of the other properties of fiber metal laminates which makes it even more better than MMC. The first is the low weight that it possesses and the mechanical properties that it exhibits. Say for instance, the main example we have is glare that is 10 to 100 times slower. It slows down or deflects the fatigue growth that is supposed to occur in the aircraft. It is also corrosion resistance as well as fire resistance. So we see over here that the fiber metal laminate can also act as a very good solution for the aerospace engineers to be implemented in the aviation and aerospace sector. Now here I've given some of the implementations of aerospace related to the fiber metal laminates. As you all can see, the most common is the glare, which is used in the upper fuselage at the leading edge of Airbus A380. On the other hand, if you see the arrow that is made of alternating sheets of aluminum alloy, it is also being used in many of the implementations, and glare is also used in the C-17 cargo doors. So we see over here that the fiber metal laminates can also be a good solutions for the aerospace implementations. Now the next thing is that we know that all engineering applications do have some limitations. So we decided to choose CMC. Now what is the special feature in CMC that makes it different from MMC as well as the FMC? The two earlier things that we are talking about. The major difference is nowhere else except that CMC have a high resistance to thermal shocks. In case of MMC, we see that whenever there is a chance of those at high temperature, it has been subjected to such type of shocks and the properties used to fluctuate. Whereas CMC can withstand a very high temperature. And it is not by words, these are written in the Material Science and Engineering and Introduction by William McAllister. The reference is taken from there. And what we did is, whenever we analyzed the CMC, we found out that we have the flexural strength and the fracture toughness with respect to the CMC material. And the next thing we did is we again plotted that data into the frame of picture, which we call graph. And over here, as you can see, the fracture toughness as well as the flexural strength is measured in both the axes. Now, the right thing for an engineer to do, as a designer to do, if I tell you to select one of them, you will be probably looking at the graph straight away and selecting the appropriate and the right material as the CMC. So, I think we came to the conclusion itself that we understood that a solution for the aerospace industry cannot be created by a single base metal, but by a group of metals known as composites. And we have reviewed in our paper that how MMC, CMC, FMC can be an effective option and a solution to identify the problems made previously, rectify them, and be a suitable material for aerospace implementations. Ladies and gentlemen, thank you very much for your patience. And here are the references. Thank you. And I believe the objective of education is the freedom of mind. So ladies and gentlemen, go ahead with your queries. I'm looking forward to it. Thank you.
Question, please. Yeah, very good presentation, but unfortunately, I don't know much about this area. So I can't ask you a question. But it's a very good presentation. Thank you. Thanks a lot. Our next